Welcome back. In this part of this lecture series on capacitors, we'll do some basic work about capacitor combinations, about introducing dielectrics into the capacitors, etc. etc. For doing all these parts, what we need to do, we need to understand how the potential drop varies as we move across capacitors and how charges vary in series and different parallel combinations. So as I told you earlier, for understanding this whole thing, it is very convenient to think of an analogy of water tanks. If you can, since we are very much familiar with these water tanks, we already know what is the answer. We'll simply transport that answer to this concept and two things will perfectly match with each other. Let's see how. First of all, let me tell you what is series combination and what is parallel combination. And parallel combinations. Think of water tanks, let's say like this, and they are connected with some water pipes. This has got some water into it, and I'm assuming this is ground level, so I'm assuming that it has got 0 joules per kilogram energy when water reaches this level. Although this is not correct, this is just a reference point. So I'm assuming the potential energy of water as it reaches the ground level as 0. And potential energy, you know, is potential into mass for gravitational potentials. So it is for, that means potential is basically potential energy per unit mass. So let's say if 1 kilogram of water or 1 liter of water is over here, let us say that it had it has got potential 100 joules per kilogram. That means if 1 kilogram of water is in this tank, it has got a potential energy of 100 joules. Let's say, just for the sake of an example, let's say over here, when water is down there, you can imagine that potential energy is going down as water flows from this water pipe from tank number 1 to tank number 2. What will happen? The potential energy is decreasing. Let's say this is whatever you call, let's say this is 80 joules per kilogram. So what would you say? As water was flowing from tank number 1 to 2 through this pipe, what was that? There was a potential drop. If you move along the water, what you will find? Potential drop. Water will tend to move from higher potential to lower potential. So, if this is 100 joule per kilogram over here and 80 joules per kilogram over here, and just for the sake of example, let's say it was 50 joules per kilogram over here, and I have already said it is 0 joule per kilogram over the ground. Now, what is the potential drop across this pipe? As water flows across this pipe, there is a potential drop of 100 minus 80. This is 20 joule per kilograms. And what is the potential drop across this pipe? You would say it is 80 minus 50. It is 30 joules per kilograms. And what is the potential drop across as water comes down to ground level? There is a potential drop of 50 joules per kilogram. So as you move along the water flow, the potential will go on decreasing. But the sum of potential drops across individual pipes is equal to what? The total potential drop. But if I say that 100 liters of water was flowing through this pipe, what is the amount of water flowing through this pipe? I'm assuming everything is already saturated. This means that this tank is full, so it cannot hold on to more water. If 100 liter flows in, the 100 liter flows again to the next tank, and then again the 100 liter flows to the ground level. That means the amount of water flowing across these pipes would be same. That would be 100 liters from this pipe, then 100 liters from this pipe, and 100 liters from this pipe. This kind of combination is called series combination. Let us apply the same thing to some circuit elements. It would be very much similar when we'll do the resistance combinations, quite similar. except the basic formulas may change, but yet the primary things would be essentially the same. Like, let's say I've got three capacitors joined like this. This is C1, this is C2, this is C3. And let's say the negative is grounded, that means this is at 0 volt and this is at 100 volts. Now what will happen? If charge Q flows from the positive to first capacitor, if charge Q is flowing through C1, what is the amount of charge flowing through C2? Flowing through C2, it would still be Q. It would still be Q for C3 as well. As much charge the battery has, the positive terminal of the battery has sent in, the same amount of charge will come back. That means charge through C1, C2, C3 will remain same. Now think of charge in analogy with water flowing through, amount of water flowing through these pipes. That means if 100 liters of water was flowing through first pipe, the same amount of water will flow through all pipes in series combination. Similarly, if charge Q is flowing through first capacitor, as long as we remain in series combination, the charge to all the capacitors would remain same. But what will change? The potential drop. Potential drop across first capacitor may be V1. It is say V2 across the second capacitor, and it is say V3 across the third capacitor, and we reach to ground level, that is zero potential. Now what is the case? The case is that 20 plus 30 plus 50 was turning out to be the total potential difference. Similarly over here, V1 plus V2 plus V3 will turn out to be equal to 100 volts. Or if I, for that matter, in general, say V, then V is equal to V1 plus V2 plus V3. So as we connect capacitors in series, the charge to each capacitor would remain same, but the potential drop across each capacitor can be different, or it can be same as well. If capacitor values are same, the potential drops across each of them would also be same, but it can be different as well. It will depend upon the values of C. We'll see how to calculate that later on. On the other hand, how a parallel combination works. Think of a water tank, and it is connected to ground through different pipes. One pipe has got the wider bore, and the other has got a thinner bore. What will happen? The amount of water which will flow from the first pipe would be different from the amount of water flowing through the second pipe. Let's say this is 1, this is 2. But if potential was 100 joule per kilogram in this water tank and it is 0 joule per kilogram at the ground level, what is the potential drop across the first pipe? It would be 100, 100 minus 0. What would be the potential drop across the second pipe? It would still be 100, 100 minus 0. So in parallel combination, the amount of water flowing through each pipe may be different, may be same, depending upon whether the pipes are same or different. It will depend upon the nature of the pipe. So the amount of water will be different, can be different, but potential drop across each pipe is same. Think of a parallel combination of capacitors now. Let's say I've got one capacitor, two capacitor connected to a battery. Now charge Q has got an option. It may flow through this first capacitor Cu1 and reach the negative terminal of the battery, or it can follow an alternate path. The parallel combination simply means that there are alternate paths available. Now the charge may also flow through this pipe and come through this side and come to the negative terminal of the battery. Let's say this was 100 volts, the positive terminal, and the negative has been grounded. That means whether the charge flows through the first capacitor or it flows through the second capacitor. What is the potential drop across it? From here to here. This end is at 100 volt, this end is at 0 volts, so potential drop is 100 volts. And what about this? Again, its one end is at 100 volt and the second end is also at 100 volt. So potential drop across it is also 100 volts. So in parallel combination, the voltage or the potential drop across each capacitor would remain same no matter how many capacitors are there. Potential across each of them would remain same. How? But the charge flowing through them would be different. Now what will happen? the total charge Q is flowing, it will get divided into two parts. Let's say Q2 through this and Q1 through this. But since there is charge conservation, Q1 plus Q2 would always be equal to Q. This is a basic information about the parallel and series combination. Now we'll solve some numericals, some general questions, and then starting from scratch, I'll keep on increasing the degree of difficulty of the questions. Let's see what we can do. First of all, I'm going to find out formulas for series combination and for parallel combination. Let's say there are three capacitors in series and there is a total voltage V applied across it. This is C1, C2, C3, and let's say the voltage across them is V1, V2 and V3. Let's say total charge Q is going through that, and I assume that the effective capacitance of these three capacitors is Cs. Now total charge is Q, total capacity is Cs, total voltage is V. I know Q is equal to Cv. So what is Q? Q is equal to Cs into V. So what is V? V is Q by Cs. Now think from individual capacitors point of view. For this capacitor, the voltage is V1 and charge is Q through it. So for Q, this V1 can also be written as Q by C1. Similarly, V2 can be written as Q by C2 and V3 can be written as Q by C3. But we know that the sum of these three voltages, that is V1 plus V2 plus V3, must be equal to total voltage V. So what do we get? V is equal to V1 plus V2 plus V3. Just put in these values. Q is common, just cut it out and you will get 1 by Cs into 1 by C1 plus 1 by C2 plus 1 by C3. So when capacitors are connected in series, what you find out? When capacitors are connected in series, their capacitance would be, effective capacitance can be calculated by taking the sum of reciprocations. They will give you 1 by Cs and you can solve it out. We'll do numerical these are simple things. Okay, what about the parallel combinations? Let's say there are three capacitors, they are joined in parallel like this, total voltage is V and total charge I am assuming to be Q. The charge gets divided as Q1, Q2 and Q3 through capacitor C1, C2 and C3. Total voltage across each of them is V. Now what do I get? What do I get? Total charge Q must be equal to Q1 plus Q2 plus Q3, and I know that this Q is equal to Cv. I am assuming Cp, that is the parallel combination, the effective capacitance of this parallel combination as Cp. Then Q can be written as Cp into V. This is equal to C1 into V plus C2 into V plus C3 into V. V is common, just cut it out from both sides and you get Cp is equal to C1 plus C2 plus C3. That means when capacitors are in parallel, you have to take simply their algebraic sum. That will give you the total effective capacitance. So now let's start with numerical problems. And as I told you, I'll start from a very basic, very simple questions. If you follow each and every step, you will be able to do all the questions. Let's say there are two capacitors, 2 microfarads and 6 microfarad. What is the effective capacitance? You'll say, okay, 1 by 3 is 1 by 2 plus 1 by 6. Both of them are in micro, so I don't need to convert them. The final answer will automatically be also in microfarads. So I can see it is 6 plus 2 divided by 12. This is 8 by 12. This is 2 by 3. But this is, remember, this is 1 by C. So C turns out to be 3 by 2 microfarads. That is the answer. What? Had these capacitors been in parallel, the answer would have been even more simpler. It would have been 2 plus 6. That is 8 microfarad. The capacitance would be simple sum of these two. Now for two capacitors, this formula you can just do it like this. It is 1 by C1 plus 1 by C2. So it will be C1 plus C2 divided by C1 into C2. This is 1 by C. So C is C1 C2 over C1 plus C2. For as long as there are only two capacitors in series, you can do it a little fast way. How you can do that? 2 into 6 divided by 2 plus 6. So 2 into 6 was 12, divided by 2 plus 6, it is 8, 12 by 8, this is 3 by 2, that was the answer. Let's proceed with some more questions. What about this? How do you solve effective capacitance between P and Q? I'll write down the values. But you should compare this question with this question. How these two questions are different. You can see these two are in parallel. So you first solve C2 and C3. There will be C2 plus C3, and then whatever comes, you'll make an equivalent diagram. Instead of writing down C2 and C3 separately, we'll write down single. Let's say I call that C dash, and this was C1. Now these two are in series, and then we'll find out the effective value as C. However, in this case, are C1 and C3 in parallel? The answer is no, because there one plate of C1 and one plate of C3 are coming to the same point, say point P, but the other end of C1 and other end of C3, they are not combined again. For two capacitors to be in parallel, the one plate of each of them should be joined at one end, at one common point, and the other plates should also be joined at other common point. Only then you can call them to be in parallel. So here, C1 and C3 are not in parallel, C2 and C3 are not in parallel. Rather, what you would do, C1 and C2 are in series. You can think of it like that. If charge Q is flowing through that, the whole charge will have to flow through C2 as well to reach the end Q. This means that the charge through C1 and C2 is same, which is the property of the series combination. That means C1 and C2 are in series. Whatever comes, you will take a parallel combination with C3. Let's proceed with some values. Whatever. Let's say this is 3 and this is 6 microfarads. Even if I don't write, let us assume every capacitor to be in microfarads. And let's say this is 2 microfarads. And over here, let's say this is 2, this is 3, and this is 6. What would be the effective value? You'll say, okay, 3 and 6 are in parallel, so I haven't touched 2. This remains same. Now 3 and 6 are in parallel, so total there will be 9 over here. And now 2 and 9 are in series. You know the answer would be 2 into 9 divided by 2 plus 9. That is the effective capacitance. That is equal to 18 by 11. C1 into C2 over C1 plus C2. What about this? Here 2 and 3 are in series, so I'll have to start with that. Their effective combination, effective capacitance of this combination is, I'm not touching this 6 microfarad for the time being, and 2 and 3 are in series, so it will be 2 into 3 divided by 2 plus 3, so that means it is 6 by 5. 6 by 5 and 6 are in series. The final answer, C, would be 6 by 5 plus 6. It is 36 by 5 microfarads. That is the answer. Let's complicate the things a little more. Let's do this question. I'm just putting anything, whatever is coming into my mind. Let's say this is 3 and this is 6 and this is 2, this is 1, this is 3, this is 2 and this is 6. And the question says, find effective capacitance between P and Q. So how to proceed with this? What you would do, You would first of all solve those parts which you are sure about. For example, this 1 and 3 are definitely in series. This 3 and 6 are definitely in series. To make an equivalent circuit, solving only these two parts and keeping everything else the same, the result would be, you would get a 2 from here. 1 and 3 in series, it will be 1 into 3 over 1 plus 3. This is 3 by 4. So I have put a capacitor of 3 by 4 microfarads over here. Now there is a 2 over here, and then I got 3 and 6 in parallel. So there is 9 over here, and then there is one more 6. I am not changing anything else. Now what you are sure about? This 2 and 9 are in series. So in the next step I will solve. Whatever I am not solving, I will keep it unchanged as such. This is 3 by 4, this was 2, this is 3 by 4, and 2 and 9 in series, it will give you 2 into 9 divided by 2 plus 9, which is 18 by 11. So this is 18 by 11, and then you have got one more 6 over here. Now what you are sure about? You are sure that 3 by 4 and 18 by 11 are in series. 3 by 4, in parallel. 18 by 11. So what do I get? It is 33 and 72 divided by 44. So this is 105 divided by 44. In the next step, I'll change this circuit to, I've got a 2 over here, I've not touched it till now. I've got 105 by 44 over there, and then I've got a 6. Now you can solve this out. What you will do? These two are in series. What would be the answer? It is 2 into 105 by 44 divided by 2 plus 105 by 44. What is the answer? The 44 I think will get cancelled out. 210 divided by, it is 88, and 105, it is 193. So in the next step, what do I get? I've got one capacitor of 210 by 193 and another capacitor of 6 over here. Yes, it's correct. And now they are in parallel. So you will say 210 by 193 plus 6. Whatever comes is the answer. So even the complicated problems can be broken down into small steps. Don't skip the steps. Don't try to skip the steps. The key idea is you need to follow the procedure to reach the final answer. Now these are the questions which you can handle directly with series and parallel combination formulas. However, these formulas can not be always used to solve certain problems. Actually, the problem remains same. You may say they are the shortcut methods, some tricks, some small steps which you can follow. So I'll give you 3-4 questions. You solve these questions and write in the comment box. Let's see if you can solve these. Can you solve this? These are easy questions. This is say 2, 3 and 4, whatever. Will you try to solve this question? I'm telling you these are easy questions. We'll go to the tough ones, but these are different ones to start with. Whatever, 2, 4, 3, 6 and 5 microfarads. Find out effective capacitance between P and Q. Can you do this question? Can you do this question? Two, 10, 3, 15 and 1.5 over here. Can you solve this? Can you solve this? Okay. like this. If I have got a capacitor over here, I've got a capacitor. Let's do it like that way. Let's do it like that way. Can you do this? This is point P and this is point Q, and this is 2, 3, 4 and 5. Can you do this question? And a little different as well. Let's say, for a capacitor, the capacity is given as epsilon naught A by D. Let's say the plates of this capacitor has got an area A and distance between them is D. And I fill it halfway like this with a dielectric constant K. Can you solve this? What would be its capacity? This is say D by 3 and this is say 2D by 3. Can you do this? The same capacitor, but upper half is filled with dielectric constant K and lower half is empty. Or let's say it is filled with some material with dielectric constant K2. Can you solve this? These are easy questions. It will not take more than 15 minutes for you to solve these 6 questions. I will come up with new problems in the next lecture. Thank you.